generalize from what we're seeing both in the Cassandra community as well as in the broader distributed database world. And the first one of those is if it's not SQL, it's not a database. So Nate just talked a little bit about thrift. We're finally sunsetting thrift, and he's a little bit sad about that, but this is a case where the market has really spoken, and not just spoken, but it's really yelled at everyone to get their attention and said, look, we really want a query language where we can standardize across the different languages and drivers that people are using, and that gives us some kind of common lingua franca. So just the history here is that in the early 2000s, people started realizing that, hey, Oracle doesn't scale. I need to start, the state of the art then was sharding to be able to handle larger workloads as people started building cloud applications, the first generation. And then in 2006 and 2007, Google and Amazon kind of kicked off NoSQL by publishing the Big Table and the Dynamo papers. And then in the years following, you had this explosion of scale-out systems, some of which are still around. These three at the bottom here are still around, and a lot more that aren't, or that they're nobody really uses them anymore if they're technically still around. So, in the bad old days, this was the world that we lived in terms of being able to talk to those NoSQL systems. In fact, you kind of had two camps in this NoSQL world. You had the people who said, I need to build a database that's going to scale, and relational databases don't, so I'm going to live with some other kind of paradigm. And then you had people who said, yeah, but I really hate SQL. And so you kind of had both of these camps, and really the first camp is the one that kind of won, that people realized that SQL actually gets the job done, and started moving towards that. In the Cassandra space, we had some direct experience with the downsides of not having that SQL API, and one of the big ones is that not only is a driverless kind of RPC paradigm too low level, but it results in fragmentation in your user community. So we had Hector, we had PLOPS, we had SDNX. Those are just in the Java space. You multiply that by Python, by C#, by Go, by Ruby, it got a lot worse. And by the way, you're seeing this today in the DynamoDB space, where they're saying, hey, we're just going to give you a REST API, and that's all you need. And people say, yeah, but that's not all we need. And they start building things like this, and it starts fragmenting. So in, I believe it was 2012, DataStax made this t-shirt for an internal event. I wish I could say that it was an exaggeration, but this was an actual thing that happened. IKVM, for those of you who don't know, IKVM is an implementation of Java VM on .NET. It was kind of a labor of love by some Scandinavian guy, I think. And he finally said, I'm done with this last year, which was kind of sad because it was one of the coolest, just pieces of technology that I'm doing this because I can. But back at this time, there wasn't a really good production-ready C# driver for Cassandra on top of Thrift, and so this guy was using Hector, but he really wanted to do .NET, so he was using IKVM, and yeah, things got messy. So in 2011, we started moving towards, in the Cassandra space, we started moving towards what can we give people that's higher level than Thrift, that's going to allow us to standardize this world that we've created. And it actually took us 3 tries to get it right, where the first CQL 1.0 was very Thrift oriented, and it operated in terms of slices of cells that you would get back. and did not take the world on fire, so we iterated. I don't actually remember what CQL 2.0 is. It was very forgettable, but in 3.0 we said, okay, here's how we're going to map rows and partitions to Cassandra's storage engine. And it worked really well, and I think a lot of the subsequent SQL-like languages in the database space have built on this model. So what you have Cosmos DB saying that they're SQL, which is, if Cosmos DB is a SQL database, then Cassandra is a SQL database. I mean, it's a triumph of marketing there. Cloud Spanner is also marketing themselves as SQL with some more justification than Cosmos DB can point to. And then you have Couchbase doing a language that's pronounced nickel, I believe. And then HBase has gotten in the game as well with a SQL, a JDBC library that, to the best of my knowledge, is Java only. So, but everyone's moving in this direction. And I say everyone, there's actually two really popular databases that are bucking this trend. It continues to baffle me how MongoDB has this reputation for being developer friendly without a real query language, but there you are. So that's something I don't really understand. I think DynamoDB, you can explain its popularity just by saying, hey, you can put in your credit card on Amazon and get a database and start using it, and it's that first party cloud advantage that really makes it popular. Lesson number 2 for me is that it takes over 5 years to build a production-ready database that people are going to want to use. So Kurt Monash is an independent analyst, and he says, rule number 1, developing a good database requires 5 to 7 years and tens of millions of dollars, and that's if things go extremely well. And our experience kind of reflects this in the Cassandra community, and for me at DataStax, I started putting this slide. I said, I'm going to put together my top 3 mistakes starting DataStax, and it started growing, and then I was like, at 5 mistakes, I'd better stop. So it's hard to build a database, it's hard to build a company at the same time. You are going to make some mistakes. But I think one of the biggest ones that I would change if I did it over again is that we did a Series A of $2.5 million. And Kurt Monash, who said it's going to take tens of millions of dollars, he said that in 2013. So even if I'd been reading his blog at the time, it was too late for me to profit from that advice. So we did our raise of $2.5 million. We started getting some support customers. This is in 2010. And we started building our management tool called Ops Center. And then in 2011, we said, hey, we're going to be out of money in another month or two. We'd better raise some more money. And the investor said, yeah, but where's the customers? Like, what have you built here? Yeah, you've hired some people who are writing open source code, but what have you built? So that was definitely one of my top lessons that I would change. We did obviously make it through. We found some investors, Crosslink Capital, who believed in our vision, even though we hadn't made a whole lot of progress since our Series A. But that was a lot of stress that I wouldn't want to repeat. So Kurt gave some examples of why it's going to take longer than you think to build, to go from, hey, I've got this research idea to now I've built a working database out of it. Concurrent workloads, it's going to get a lot hairier in real life than whatever you can put together in a lab. Minor edge cases turn out not to be minor. These are true. I would add some specific examples from the Cassandra space. Those of you who've run Cassandra in production know, hinted handoff, repair, counters. Maybe if you're newer to Cassandra, then maybe you missed the pain with counters. I think we finally got that pretty right, but it took us 3 major rewrites to get there. Lightweight transactions, another thing where it's pretty solid now, but it did have some growing pains. And then just building a test suite takes longer than you think. In fact, I think everything on this slide has had multiple major implementations, and it's just hard to get right the first time. So just as an aside, one of the things we're working on at DataStax to kind of address that last point of, I need to have a test suite that will help me understand real world use cases and detect problems before customers hit them. So we've built a tool called Fallout, and the simple way to think about it is Jepsen at scale, for those of you who are familiar with Kyle's work on Jepsen and testing databases with that. And so we have the concept of a set of clusters that participate in a test and a workload that are going to act against that set of clusters. And we define phases that run in parallel, and then we have a set of correctness checkers that run after that test. So here's what a very simple workload looks like. So I think you can read that. It's a little bit small, but basically what we have is we've got three major sections. You've got the ensemble, you've got the phases, and you've got the checkers. And so what I've got is I'm defining a simple 3-node local cluster using CCM, and I'm going to insert data using Cassandra stress while I'm bringing gossip up and down. So you see in the middle section, I've got gossip up, down, command disable gossip, secondary command enable gossip, and then I'm just going to do that randomly across 30 seconds here. And then I'm going to be doing some reads in there at the same time. And then after the test is done, I'm going to go through and I'm going to verify that actually, I'm getting the data out of it that I thought I inserted. So this is a very flexible way to compose the kinds of things that you see in the real world, where you have a bulk load happening while I'm adding a node to the cluster, while repair is running, while some of the nodes are compacting. And that's the kind of thing that don't often get turned up in simpler testing approaches. So it's coming back to the lesson here of 5+ years. Cassandra became an Apache top-level project in February 2010. We released 3.0 in fall of 2015. So I'd say that's right around that 5-year mark, where, as Nate said earlier, 3.0 has served us well. It's been a very stable release and a release that delivers the features that people need to build cloud applications. And then the last bullet point here, I think a lot of people in the open source community like to think that, hey, we're special because we're doing this with open source, so the rules don't apply to us. But open source doesn't change this kind of rule of, here's the laws of physics and you can't go faster than the speed of light. Open source doesn't actually make your database better, faster. I wish it did, but it doesn't. But what it does do is it lets you get adoption. So there, before NoSQL really got its legs, there were a bunch of databases in the early 2000s that were trying to solve this, I need to scale my database problem. And for the most part, nobody's heard of them. Because they were going after this, hey, I'm going to raise some money and I'm going to build a proprietary product and I'm going to go try to convince people to use that. And it's really, really hard if your name's not Oracle to get companies to buy an untested database from you. And so open source really kind of shortcuts that problem by giving them that comfort level of, hey, if the company behind this dies, at least the source code is there. I can hire engineers to work on that. So it gives them that security blanket that it's not a magic wand. You're still going to have people being very risk averse with their data. That's their most important asset. But it does, for the people who are desperate enough that I'm in so much pain from MySQL not scaling that I'm willing to try something new, then it gives you that edge. Lesson number 3, the customer is always right. And here's what I mean by this. I think, and I will raise my hand as being significantly responsible for this in the Cassandra community, but as engineers building a database, we tend to have the attitude of, if the database broke because you did something that you weren't supposed to do, then it's your fault. And that's a mindset that we need to get away from. And it stops us from learning what what problems people are trying to solve as quickly as we otherwise could. So as an example, I'll give a couple examples. So in 2012, if you did a sequential scan like this and said, hey, I've got billions of rows in showing what products from my catalog users have bought, then I will run the server out of memory doing that sequential scan. This was 5-6 years ago. It would try the early versions of CQL would materialize the entire result set into memory and then hand it back to the client. So if you're going to try to pull that, pull 100 million rows into memory, that it's going to fall over. So we took a step back and, our first solution was, hey, you shouldn't do that. So we're going to add this check that says, if you're doing a sequential scan, I'm going to reject that. And I'm going to say, well, if you really do need to do that sequential scan, then use this magic incantation called allow filtering. And so what people, there's that saying that the internet resists censorship, interprets censorship as damage and routes around it. Users interpret warnings as damage and route around them. And so the quickest way to route around this warning is, okay, copy, paste, allow filtering, I'm good. And the reason this is really insidious is that this will work fine with a toy data set on your laptop. And then you go to production and everything gets slower and slower, and then finally one of your servers OOMs and falls over. And so it gets you into trouble. And so the warning was there for a reason, but users aren't looking to understand the guts of the database. They just want to get their job done. So we had to take a step back and say, okay, how do we solve this problem in a way that lets users do what they want, but it's also going to stop the server from falling over? And that's where we added paging to the native protocol, where instead of giving back the entire result set, I'll just give them back 1,000 rows or so at a time. And that worked a lot better. Another example, and this one, so spoiler alert, this is something that I don't know the right answer to yet. When you're doing deletes from Cassandra, we need to generate what's called a tombstone that says, this row doesn't exist anymore. And then when I'm replicating the delete to the other replicas, then that tombstone is what lets me ensure that none of the other replicas say, oh, hey, you're missing this row, let me give it to you. The tombstone serves as a marker to say, no, it's actually been deleted. You're the one who's missing the delete. Let me hand you that tombstone record. And so that's great. The problem is that when I'm doing this and I'm reconciling the results from multiple replicas, I need to include the tombstones for rows that don't exist anymore in my response. If I'm doing a scan across a series of rows that includes some deleted rows, I need to include those tombstones. Otherwise, again, the server's going to, or the coordinator's going to combine the responses from the different replicas and say, oh, here, this replica A had this row that replica B didn't know about. So clearly, replica B needs to get that row, and I'll hand back the client the result, including that row. So the tombstones need to participate in that query response. And that means that, again, this is something that we're pulling those tombstones into memory and handing them back to the coordinator. So there's a potential for the server to fall over and run out of memory. And so we said, okay, we will take a similar approach here. We'll add a warning threshold and an error threshold and say that if your request generates or it scans in more than 1,000 tombstones, we'll write a warning to the log. If it scans in more than 10,000, then we'll just fail the request and we'll stop processing it. And so the obvious problem here is that if I'm a developer working at my laptop, I'm typically not tailing the server log to check the warnings that it's generating. So this is, it's kind of our best effort as server developers, but it's not super useful. So I would say one of the morals of this story is we need to add something to the native protocol to be able to send not just errors back to the client, but warnings. so we can get ahead of problems like this. But that's not the real solution. The real solution is that we need to get tombstones out of the system much faster. We need to get it down from days or weeks, which is how long it takes to run repair typically against a large cluster. We need to get it down to hours. So I think there's three components to that. First, we need to get rid of this kind of hack that we have called GC grace seconds that says this is how long I'm going to wait until I assume that everyone knows about this tombstone, and then it's okay to garbage collect them. So we need to, and the real answer of when it's okay to collect a tombstone is once it's been repaired and we know it's on every replica. So we need to track repair status on a token range level so that we can purge tombstones more aggressively. And then we need to make repair actually fast enough for that to be a meaningful difference. So this is why this is marked year question mark when we'll be able to deliver this. But I think that's the right thing to do here. That's the real solution and not a Band-Aid. Another example is joins, and this is an example of where we started off by saying if you're going to scale out and you're going to partition your data across multiple machines, then you want to satisfy your requests from one machine at a time. You don't want to have to correlate data from multiple machines. And so we're not going to do joins. We're going to encourage denormalization. We'll give you collections. We'll give you user-defined types to enable you to denormalize more easily. But what we're seeing is that people are still doing client-side joins. People are saying, you know what? Denormalization isn't always the right answer. And since you're not giving me joins in CQL, I'm going to do it in my client code. So that's something where I'm still not sure that we should be giving people joins, but maybe we should think harder about that instead of saying, no, you're doing it wrong. So one of the attempts we made is we said, OK, we'll give you materialized views that are going to make it even easier to denormalize. Again, the implementation has proved tougher than we thought, but I still think it's a useful construct, but I'm not convinced that that's going to solve the demand that's there that people are asking for. And there's some prior art now where there wasn't 5 years ago. So both Google Cloud Spanner and Microsoft Cosmos DB, those both came out last year, and they're both unapologetically saying, hey, we're going to let you do joins. And so there's two objections to joins. One is the performance objection that I mentioned, but the other objection is that if I'm not guaranteeing ACID consistency across multiple rows and across multiple partitions, then isn't it dangerous to be giving people joins? And so Cloud Spanner is out there saying, yes, that's absolutely dangerous, and that's why we're going to be all ACID all the time, two-phase commit across Paxos replication groups, and we're just going to solve that problem that way. Spoiler alert, not a spoiler alert. I'm actually have a slide about this in a second. That's the wrong solution, by the way. But Cosmos DB said, hey, we're not giving you cross-partition ACID, and we're going to give you joins anyway, because that's actually useful even if you're eventually consistent across partitions. And again, that's what people are doing in the wild. People are building applications, doing client-side joins that are eventually consistent across partitions. So I kind of think we need to get over it and start thinking about adding joins. And as I have on the slide, we could take baby steps there if we wanted to. We could add joins within a single partition only. That's still significantly useful, but it's not going to open up the can of worms of performance and consistency the way cross-partition would. And then finally, words of wisdom from an elder statesman of NoSQL that I haven't lived up to very well. But I still think this is true, that every time you're adding a feature to Cassandra or to your infrastructure, and you say, this is really hard to figure out what the right value for this performance parameter should be, I'll just make it configurable. That's probably the wrong solution. And that gets me to my next topic, which is that just enough magic is good. That's what customers want. but too much magic is bad. So some of this is that people are going to tell you what they think you want to hear, and even when that doesn't make sense. So every year or so you have a company that says our database has figured out a way to defeat the CAP theorem, and we are both consistent and available even when network partitions happen and nodes go down. And then it's like the game you play is, okay, let me read your architecture and figure out where you screwed up, because it's not just a good idea, it's the law. Or another one, our queue can guarantee exactly once delivery. It's basically a variant of hey, we've defeated the CAP theorem. Or another fun one is just to read the fine print when vendors tell you we have an SLA with this many nines. For instance, one of the cloud database vendors says we have a 4 nines availability SLA. Fine print, if we don't achieve this, we will refund 10% of your money. So I take away from that, you don't have a whole lot of faith in your SLA that you're advertising. But it's not just about over-promising, but even if you actually promise something and deliver it, it's not necessarily a good idea. So I think one of the best examples of this is a feature that the researchers at Brown added to HStore in 2012. So HStore was, for those of you familiar with Mike Stonebreaker, CStore was the columnar store that became Vertica. HStore is the horizontally partitioned database that became VoltDB. So there's that kind of naming convention that he likes there. But they added a feature to HStore that says, hey, if you tell me your queries implemented as Java stored procedures, I will automatically generate the optimal partitioning for your data, and I'll spread it across my cluster according to that partitioning. And some of your transactions are going to be cross-partition, and those are going to be slower. But I've done my best to minimize that, and in fact, I can prove that my partitioning is better than anything you could come up with if you tried to tweak it manually. So this is a really cool idea. The problem is that users looked at that and said, wow, that's actually really confusing because literally I don't understand when my transactions are 100 times slower than they usually are. So when I have to fall back to a two-phase commit across multiple partitions, it gets really slow and it's not obvious at all why. So this is a case where there's this magic solution and it does what it's promised, but users don't like it anyway. And so you can see that the state of the art in databases today, you've got Cassandra, you've got Cloud Spanner, you've got DynamoDB, you've got Cosmos DB. I think those are the 4 most relevant databases today. And they all use explicit partitioning where the user says, here's what I want my partition key to be, and the database respects that. A couple years ago, Google announced that Cloud Spanner was coming really soon, and some people at DataStax asked me, hey, what should I expect from Cloud Spanner? Should we be scared about this new competitor? And basically what I wrote was, Google's actually been really open about how Cloud Spanner works. And just from the architecture, you can tell that it's going to be really slow on writes. And not only that, but the writes are going to slow down reads as well, because there's going to be some interference there. And both of those predictions turned out to be absolutely correct. And late last year, Todd Lipcon at Cloudera did a benchmark of Cloud Spanner against Apache Kudu, which is a hybrid transactional analytical database that he works on. So one of the interesting things about this actually is that unlike Cosmos DB and DynamoDB, where you pay by here's how many requests per second I want, Cloud Spanner actually charges you by node. So you can actually take the node pricing that Google gives you and you can stand up a virtual machine with similar specs, and you can do a more or less apples to apples comparison there. So that's really useful and very kind of them. The problem is that Cloud Spanner doesn't come off looking very good when you actually benchmark it. And my guess is that Cassandra is probably around twice as fast as Kudu. That would be my guess. So we're talking 50 times slower than Cassandra. And this is a result. So this is a result of Google promising magic and delivering it, in the sense that they're saying, if you want ACID transactions across multiple partitions, we will give that to you. And they do. The problem is that the price you pay is unacceptable for most applications. One more bit of magic. I'm going to pick on the cloud vendors one more time here. With the auto-scaling in DynamoDB. And the way this works is when you say I need this many requests per second and I need this much storage, then DynamoDB divides that up across what it calls partitions. I'm going to call that PP here for physical partition, which is not the same as a logical partition. Logical partition is, that's my partition key on my table. This is like a shard. A shard might be a better word here. And so there's a formula for how many shards it's going to create. And then there's two problems with this. One is that as you grow those shards, as they grow beyond 10 gigabytes, that's the limit, then it's going to split into two, and each of those two new shards is going to have half the operations per second that the parent shard had before. And so you can have this kind of, instead of all of my shards have the same request ceilings, which is relatively easy to understand, you can have some shards with a factor of 2 or 4 or even 8 times less, which starts to get hard to understand. But there's another implication here that's, I think, even more problematic, which is around bulk loads. So if you can over-provision for a bulk load. The problem is that when you scale back that over-provisioning, things don't work the way you'd expect. So here's an example with a little bit of math. So I want to bulk load 200 million 1 kilobyte items, and I want to do that in an hour. So I need a write capacity of 55,000 requests per second, and that's going to translate into 55 physical partitions. So I do my bulk load, it takes an hour, I'm all good, and now I want to dial back my requests per second to 1,000. That's my steady state of my application. I don't want to be paying for a lot more requests per second that I'm not going to be using. But that translates to 2 requests per second per physical partition. Or if you want to think of it in terms of the number of items that I loaded, it's 2 requests spread across 3.6 million items. So if you have any of those groups of 3 million items that have more than 2 requests per second, then Dynamo is going to say, sorry, you're over quota. And so this is something that surprises people. And a company called Ravelin says, gave an example of where they ran into this and said, we've got our partitioning scheme. It works the way it should. There's no hot partitions. There's no, it's a very fine-grained partition with high cardinality. But we still run into this because of this dynamic where the requests per second are spread across these physical partitions at a very low level. And it's really easy to exceed that just by random osmosis through your workload, and not because they're what you would think of as hot partitions in a normal sense. So the question is, and I don't have a good answer, so this is more of a question to think about than me standing up and saying I've got the answers. How much magic is too much magic? So apparently people think that joins are a good level of magic to have. Auto-scaling, I just dissed on it here, but people are voting with their feet, and a lot of people are running DynamoDB, and they're unhappy when they run into this surprise here, but they get over it, and they pay extra, whatever. They're okay. They're apparently okay with that. Not okay with automatic partitioning. Not okay with the performance penalty of full ACID transactions. I'm putting a question mark there, but as near as I can tell, Cloud Spanner has not taken the market by storm. So I'm going to say that generally speaking, people are not okay with that. So I think the overarching concern is, how can we help people understand what is going on inside the system without overwhelming them with details that they shouldn't have to care about? So that's something to think about as you're building a database. Then lesson number 5, it's the cloud, stupid. So it's 2018. At DataStax, we see over 70% of our customers with at least some deployment footprint in the cloud. I'm sure Aaron from the last pickle has similar stories to tell, that people are overwhelmingly choosing the cloud as my infrastructure environment of choice. So Cassandra was ahead of the market in some ways for a number of years. So the 2011 Cassandra Summit was actually held here at the Mission Bay Conference Center. And one of the slides we had was this one that said, blah, 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 cloud. And we're the only database that's going to support multi-data center across cloud, across on-premises. And the market kind of looked at that and said, yeah, that's cool, but why do I need that? And then when we were in 2012, we were expanding on that and saying, hey, with Cassandra, all the replicas are equal. There's no failovers that need to happen, whether that's within a data center, whether it's across data centers. Everything's active, multiple data centers in the cloud. And it was really an uphill battle for us. I said at the beginning that we had a lot of trouble raising our Series B, and a lot of that was investors were saying, yeah, but who's going to actually need this? That's really cool technology, but Amazon's got Dynamo, Google's got Bigtable at the time, Twitter's using Cassandra, but that's cool, but how many more Twitters are there out there? And so there was a lot of skepticism that this was something that was going to go mainstream. So 2018, like I said, we've been vindicated. The cloud is here. The danger is that we get complacent now and say, hey, we're the best database for the cloud, so of course you should use us. So it's time to start thinking about, what do you do when your database not only runs in the cloud, but runs only in the cloud or runs mostly in the cloud? What kind of optimizations can you start making when you're designing for that kind of world? So at the Amazon Aurora team, so Amazon doesn't give a whole lot of details about how their stuff works. But this is an exception, and it's actually a really, really good paper. This is the Bigtable paper of 2016 is what it is. Everyone who's interested in distributed databases should read it. And basically what it says is how Aurora says, instead of having, Aurora is a MySQL and PostgreSQL compatible relational database. And Amazon said, hey, we are spending a whole ton of money on networking and replicating between the MySQL masters and the MySQL slaves, and it's really inefficient because I write a full copy to disk on the master, I send a full copy over the network to each of the slaves, which each writes a full copy to its disk. All of those disks are network attached storage. That's the way Amazon likes to run things. So I'm sending, if I've got 3 replicas, I'm sending 5 or 6 copies over the network to disk. And so they said, well, what happens if we push that replication down to the storage layer instead of, and we're going to separate out that storage from the compute and serving layer. So this is, I think this is something that we need to seriously consider, and this is a little bit of a sacred cow in the Cassandra community because we're used to people coming from the relational world running on big SANs and saying, hey, that SAN is a big single point source of failure. You need to be running against local storage on lots of smallish nodes, and that's going to give you the best availability and the best performance and the best cost. But in the cloud world, I'm not sure that that's the best way to build a database anymore. This is Andy Pavlo. He's a professor at CMU. And he just did an interview with, I don't remember the publication, but he says, one of the big trends I see in databases is people are going to need to separate storage from compute to get the best performance. And he didn't specifically say in the cloud infrastructure world, but I think that emphasizes the point. So again, in terms of I don't have all the answers, but here's some questions to think about. What kind of infrastructure, assuming there are a lot of people who want to use Cassandra that do want to run their own infrastructure. So if we're going to start adding cloud native features, how do we let people running on premises start to leverage those as well? Another question, is a yearly release process or every 2 years release process or every 3 years, when is 4.0 going to be out, Nate? Is that the right process for someone building a cloud service? Or maybe even a bigger issue, what does open source look like in a cloud-first world? Redis Labs was in the news recently. They relicensed some of their software, not Redis Core, but some of their enterprise modules with what's called the Commons Clause. And that's basically an attempt to let a vendor like Redis Labs create a market for their software that doesn't just get cannibalized by Amazon and Microsoft. I've heard a factoid that Amazon makes more money from MySQL than Oracle does. I don't know the source of that, but I believe that it's true. So the Commons Clause basically says, you are allowed to use the source, you are allowed to deploy it locally, you're allowed to modify it, you're allowed to distribute your modifications. What you're not allowed to do is sell it. So it is a very specific and targeted addition to the BSD license that Redis Labs runs on that's targeting the cloud vendors. And then a question that I've heard is, well, what about the AGPL? Doesn't that do the same thing? It's different. The main differences are the AGPL just says, if you deploy this as a service, you must distribute your changes back to the community. So that would definitely make an Amazon Cassandra service friendlier to the community, but or an Amazon Redis service, but that's still not something that Redis Labs wants to see Amazon monetizing their code. Cassandra's in a different situation with the Apache Foundation. The other difference is that the AGPL has a patent clause that a lot of companies aren't comfortable with, and the Commons Clause is basically just it's like a writer that you can attach to a BSD or an Apache license without invoking the provisions of the AGPL that companies have problems with. So I'm not necessarily endorsing this Commons Clause, but it's an example of how companies are trying to wrestle with and come up with solutions to what does infrastructure look like in a cloud-first world. So in summary, if it's not SQL, it's not a database. It will take 5 years, over 5 years, to build a production-ready database if you're thinking of starting one. Do listen to your users, but when your users ask for magic, be careful because too much magic is a bad thing, and it's the cloud. And finally, number 6, we're hiring. If you're interested in working on this kind of problem, then please come and talk to me. Thank you.